Good morning, everybody. My name is Chris Bradshaw. I'm the Business Development Specialist for the Analysis Solutions. I guess, Guido, you have already introduced me, but it was in German, so I didn't understand it, I'm afraid.
I'm sorry.
Okay, so I will start off, and as per the agenda, I will first of all just introduce the FEA tools for anyone who's attending this meeting who wasn't at the user group and who isn't familiar. And I will just introduce what FEA Tools is and why, well, what benefits this program will provide. So I have a very short, so there's only a few slides in this PowerPoint here on what FEA Tools is. And really the reason behind FEA Tools is to improve your code design. And the reasons for this is because in the design codes, the B31 codes and the EN13480 code, for example, these are the two codes which I'm using as example codes, but it's not limited to these codes. But the basic point here is these codes are based in some areas on older technology. Some of these technologies are from the 1950s, where, for example, a computer was very large and took up an entire room. And because this technology is old, it's less accurate, and the technology and the information that we're talking about here is related to the intersections in your piping system, specifically the calculation of the stress intensification factors and the flexibilities of the intersections. And because these intersection stress intensification factors and flexibilities can be, in some instances, inaccurate, then you have the option, or not the option, you have the possibility, rather, to exceed or go over your safety margin, following the black line shown here, which, of course, that is not what you want to be doing. But now, it's 60 years later, 2014 now, we have much better technology available to us. The computer, back to my analogy, is obviously much smaller and more portable than it was in the 1950s, and of course much more powerful. So we have a lot more technology available to us, and we can get more accurate data, and we can then follow the green line on my little chart here, so we don't exceed and go over our safety margin. And that's really what we're all about here. So just to reiterate, the design codes, there's a lot of design codes within CAESAR II, and one of the most common of those is B31.3. But that code and all the rest of the B31 design codes have the old 50-year-old technology. Now we have the best technology, better information. And ASME recognized this as well, and they commissioned a project called STLLC0702 the intention of this project was to update and review and harmonize all the data for these stress intensification factors across all the B31 design codes. Now that project, STLLC0702, was awarded to Pauling Research Group and Tony Pauling, who is the president of Pauling Research Group. And Tony Pauling, if you are not familiar with Tony, I believe Tony's on the line. Is that correct, Guido?
Yes, I'm here.
Oh, hi, Tony. Hi, good morning.
Good morning.
Good morning. So anyway, Tony is was the original author of CAESAR II, and he's also the author or co-author of FE Pipe and Nozzle Pro finite element analysis tools for our industry here. And the STLLC0702 project was awarded to Tony and his team. And what they did a lot of analysis on intersections, and they also did a lot of physical testing. They have a test rig over in their laboratory over in Houston. So there's a lot of physical testing as well as computer analysis done while undertaking this 0702 project. And one of the indirect outcomes of the project was this FEA Tools program, which we're going to talk about today. And the, not quite sure what happened there. Well, that was here, wasn't there? Okay. So the FEA Tools program, and what we're going to focus on today is just one of the modules from the FEA Tools program, the CAESAR II FEA Translator, which is shown here. And what this translator will do is very, very simple to use, as you will see shortly. But what this table will do is it will provide more directly applicable data. And here we just have a screenshot from B31.3, Appendix D, stating that you should only use the data in Appendix D of B31.3 if you don't have any more directly applicable data. There's also a note here that the validity for D over T of less than around 100 is, what's happened there? I will just ignore that for the second. So where was it? Oh, yes, the validity of the stress intensification factors from Appendix D of B31.3 are demonstrated to be valid for, it states here, D over T ratio of less than around 100. And I also have EN 13480 shown here because I know we're in Europe here, and this may have been an ASME project, but EN 13480 has exactly the same statement here, in the absence of more directly applicable data. So both of the design codes and all the other design codes that we use all have a similar statement. If you have better data available, then you should use that better data, and FEA Tools will provide that better, more directly applicable data. So I'm talking here about FEA Tools. You hear the term FEA and maybe that worries you. Maybe you think, okay, this is complex equations and brick and shell models and so on, and maybe you're not an FEA expert. I'm certainly not an FEA expert. So all this finite element analysis, it can kind of scare people. But you don't need to worry, because the FEA Tools program does all of this behind the scenes for you. You don't need to have, for the FEA translator, you need zero finite element analysis knowledge. So you don't need to be concerned. So just to finish off, what is the current problem with the design codes today? Here we're looking at B31.3 Appendix D. And the problem is that something's got shifted across to the side here, but the problem here with the Appendix D B31.3 is the column that is highlighted here, although something's got shifted, but it's the flexibility factor, rather, the K value. For intersections in B31.3, Appendix D is a value of 1. There is no flexibility for intersections. And that's just not the case in reality. According to this, the T's are rigid bars, such as this one here. But that's not the case. If you can imagine, for example, a drinks can, and if you were to, something's gone a bit strange here. If you were to stab your drinks can with a pencil, for example, little violent, but if you were to stab your drinks can with a pencil, as in the diagram shown here, then you'd be able to move that pencil around. You could wiggle that, whether that word translates well to German, I don't know, but you could jiggle that pencil around. It would not be rigid. And a T is effectively the same thing. Maybe T's have a little thinner wall than where was I? Okay, something's causing some slight issues here with my machine, but okay. So what I was saying was you would be able to move that pencil around, and a T is effectively the same thing. There is some flexibility in there in the T. They're not rigid bars. Other issues with the Appendix D is these stress intensification values can be incorrect. And in fact, here's a note, note 11, which says, I thought that would highlight something, the outer plane stress intensification factor for a reducing branch connection with a D over D ratio between 0.5 and 1 may be non-conservative. And the last sentence there, selection of the appropriate SIF is the designer's responsibility. So the code there is also acknowledging that in some instances your stress intensification factor may be non-conservative. And this is not a new discovery, new findings. It's been identified for a while. There's a number of publications on this, and one of the really good publications on this is Welding Research Council Bulletin 329 by Rodebaugh, in which they discuss a number of the issues with the existing code values and the assumptions. I'm not going to go through all of these, but here's just a few of the, shall we say, highlights from this. For example, using intensification factor of 1 for a torsional moment can lead to inaccuracies greater than the outer plane branch inconsistency that was just mentioned in note 11. And here's an example, and we'll just take a brief look at one of the other modules of FEA Tools, the IK calculator, where you can input T geometry and you can get an instant idea of what the stress intensification and flexibility factors would be. And automatically. Here we go. So here we can get a good idea of, or instant feedback on the intensification factors and flexibility. So here's just we'll see this a little later on, here's just a extract from that table for I forget what size this T is here, but you can see according to B31.3, the bottom table, there is no guidance on calculating a torsional intensification factor, so these would all be a value of 1. But in reality, for a unreinforced fabricated T, for example, the torsional intensification factor for the branch can be 7.1 for whatever, I forget what geometry this is here. So here already you're underestimating by over 7 times on the torsional moment, just because you're using inaccurate data. Another assumption here that is wrong is well, here you can read the statement here. For run moments on branch connections with a small R over R, the B31 relationship in plane is 0.75 out plane plus 0.25 is at best reversed, and in effect the code requirements are obviously silly. Now then, that's not us saying that. That was the statement in WRC 329. Now, here's an example of this. According to B31.3, we're massively overestimating what the intensification factors are here. For example, for this geometry, again, I forget what geometry this is, but I'm going to look at an example in a second. So B31.3 says that the intensification factors for the run pipe in plane and out plane 6.9 and 8.9. Well, let's call that 7 and 9. Whereas 0702 actually comes out with, well, that's 2 and 1.1. So here we're overestimating this by quite a considerable amount. Let's illustrate that with an example. Here it's to do with small branches on a large header pipe. So this is a 24-inch system, and there are 2 small 2-inch branches around this guide here. Now, a lot of the times, maybe you would just not include those in your analysis, those small 2-inch branches. And if you do that, then everything is fine. Running the analysis on this, we get 22% of the allowable as the highest stress in the system. Everything's fine if we don't include those two branches. But if we were to include the two small 2-inch branches, as here, then we have to include the intensification factors. And these are, according to B31.3, 7 and 9, as we just showed in the previous slide. But they're also the intensification factors on the header pipe as well. And that's what WRC 329 is calling obviously silly. Those little 2-inch branches are just simply not going to have that much of an effect on the large 24-inch main. And as before, 0702 actually says these should be around 2 and 1.1, which they seem much more sensible. Now, if you were to include the B31.3 intensification factors, then you actually get a code stress failure here in the expansion case, just failing 103%, and the failure is on the header pipe itself, not on the branch, it's on the header. In reality, are those two tiny little branches going to have that much of an effect on the header? Well, no, that's what is the obviously silly. So if we were to include we get a failure with the B31.3 SIFs, but if you were to include the 0702 SIFs, then everything is much more sensible, and it's actually much more closely aligned with if you didn't include the little branches as well, at all, rather. So that's the stress intensification factors. In addition to that, we also include some flexibility factors as well. I mentioned the T's do in reality have flexibility. According to 0702 they don't. So we use the term the flexibility factor, and bends have used a similar term for a long time. A bend with an arc length of L and flexibility factor of, let's call it X, rotates the same amount with a given moment as a straight length of pipe, X times L, flexibility factor times the arc length of the bend. And it's a similar concept for T's. A T with a flexibility factor of, for example, let's call it Y, gives you the same flexibility as a straight length of pipe, Y times the outside diameter. So for example, this T here, 324mm OD, flexibility factor of 5, that T will provide us the same flexibility as 5 times 324mm, or 1.6 meters of pipe. So you can take credit for effectively adding 1.6 meters of pipe by including that T, which B31.3 doesn't give you that credit for that flexibility. So how do you do the flexibility? Well, currently there is no flexibility. This is how you model a T, of course. But if we were to apply flexibilities, you could model your T in a different way, like so. There's a few extra nodes here. There's a node added where the branch meets the run wall, and A to B is a stiff connection. As you can see here, the green line. That would be a rigid connection. And then we have flexibility applied at B and at both sides of A. That's with the, as you can see here, this symbol here, which is a CAESAR II node and a C node with a stiffness. And then the stresses and moments are calculated, as shown here, dependent on the D over D ratio. So that's how you could model your T's to include this flexibility. And that's what the FEA translator does for you automatically. So very, very easy to use. You take your CAESAR II model, build it in the normal way as you would right now, pass it through the FEA translator, which will locate all the intersections in your model, calculate the intensification factors and the flexibilities, and put them back into your model automatically, so you have a second copy of your model with the more applicable data. And what's the effect of that? Well, the forces and the moments and the stresses in your system will get redistributed. A lot of the time this means it gets reduced. It doesn't work in your favor 100% of the time. Sometimes things may increase, but the point is it's more accurate, and that, of course, you're going to want to know if things become better or worse for you. Okay, so are there any questions so far at the current moment? I don't know, do I see the questions?
Yes, there is one question.
Yep.
What is the link to the download to download the files? So where can we download the files in general?
I don't know, Guido. I think that's more one for you than me. I don't know where the link is for the files.
The download
Guido?
link. Yes, can you hear me? Hello?
Yeah.
Yes.
Okay.
Yes, hello.
The download link is embedded on the ICAS community, but if not, it is also available on the box.net account. So I need someone who needed to send me an email. I give you the download link directly.
Perfect. That was all the questions I had so far.
Okay.
Im Moment sind keine weiteren Fragen. Haben Sie noch weitere Fragen? Dann dürfen Sie die gerne rechts in Ihrem Frage- und Antwortfeld eingeben.
Okay, so is everything okay so far then? Janine?
I would think so. I would just go ahead.
Okay, so you're happy for me to continue on with part 2, the example? Yeah? So I'll now introduce our example and the overview of the situation. So the example, and if you have downloaded the files, and for those of you who are running the evaluation and have the files and are following along with this, then you should have, or you hopefully have downloaded the file. And this is the CAESAR II model that we're going to work with. Now it's an example supplied to us by a customer, so it's a real system, it's not one that we've made up. This particular one was supplied to us by Jacobs, and it's a very good example for showing FEA tools because there are a number of things which the normal code guidance for B31.3, you can see this is a B31.3 system, the normal code guidance tends to fall down somewhat. There's a number of branches here, as you can see, and a lot of these are laterals, and well, the laterals, they're not covered very well by the design codes. There's no guidance given on this type of geometry within B31.3. In addition, we also have large diameter and thin wall pipings. The D/T ratio is very high. So in some places, the D/T, diameter over thickness ratio, is over 250. And the note 11, which I pointed to in the presentation, note 11 of Appendix D states that the intensification factors are valid for a D/T of less than 100. So we're considerably higher than that. Also, the branch to run diameter ratios, the D/D, is below 0.3 in some places. So all of these instances tend to be areas where the design codes fall down: laterals, high D/T ratios, and low D/D branch to run diameter ratios. So here this is our system, and first of all let's just run this system with the standard B31.3 CIFs that I've already pointed out we should be a little concerned about their accuracy, and see where we are. So I'm just going to do a batch run with the load cases that are currently set. And okay, something may have gone a little bit strange here because when something went strange with the drivers when I switched over to presenting in the meeting. So I'm just going to, I think, kill CAESAR II. and I'll start CAESAR II again. I had to unplug and reinsert my ESL. The drivers went a bit strange when I switched over to presenting in the meeting. It's okay now. So, as I said, let me run the analysis. That's a little happier this time. So, now looking at the output, you can see straight away, I don't know if any of you are using, or which versions of CAESAR II you are using, but this is the 2013 version, which introduced the colouring of the load cases in the list red if there is a failure or an overstress. And the sustained and the expansion load case are both red, so they're both overstressed. Let's take a look at the stresses report to see this. Well, this is the sustained load case. The highest stress is 246% at node 180. And we'll go and see where node 180 is in a minute. But if I just order by the stress ratio, then you can see that node 180 and node 2110 are the only two locations which fail. Everything else is acceptable, it's no longer overstressed. And here we notice, or you may notice, that we have some reasonably high stress intensification factors. These sifts here are 16.8 and 22 for in and out plane at 180, and 14.9 and 19.5 at 2110. This is our only failure, and we've got pretty high intensification factors here. Let's look at load case, the expansion load case first, and then we'll see in the model where those locations are. So we've got a few more areas which are failing in the expansion case. I'm not going to read through all those, but you can see there's quite a few locations which fail in the expansion case. So let me take a look at a 3D plot so we can see where we are concerned about. Oops. Okay, let me go back to the sustained case first of all, and here we go. So this area that's red, that's where we have a failure. If I put the node numbers on, we can just about see. A little crowded, but here we are. This branch here, this is node 180, where this lateral is connected to our header. This is where our problem area was, node 180. And these sifts were pretty high around here at node 180. That was our first area, and the second place was 2110, which is around the back. If I go around to the back, here we see again at node 2110 we have a failure. This is on this T connection here, and again we had pretty high sifts. Remember, this is the sustained load case that we're looking at here. So this the locations where we've got failures are the supports around this area. It's just the intensification factors are very high, so maybe that's probably what's contributing. Because the let's go back to node 180. Let's see if I can find it, because this is the worst one. And here we are, node 180. So the run pipe, you can see from the tooltips, the diameter is 1200 millimeters, and it's only 5 millimeter thick on the run, and the branch is 500 millimeters and 4 millimeters thick. So our D over T ratio here is 243, very, very high, and the D over D ratio for the run to branch is 0.417. Plus, this is also a lateral connection, and all three of those situations are just things which aren't covered very well by the design code. So this is really somewhere where you would really look at obtaining more applicable data. Similarly, at node 2110, let me go back around here to 2110, 800 millimeters OD, 4 mil wall thickness, and this is a straight T, so the D over D ratio is 1, but our D over T ratio is 812 over 4, which is 200 over 200, 203 is our D over T ratio. Again, we're quite a way outside of the areas where the code says the SIFs are valid up to 100. We're over 200 here, so again, this node 2110 is really somewhere where we would look at obtaining more applicable data. Let me turn the node numbers off because it's a little crowded, but and let's go to the expansion load case. And there are quite a few areas of failure in the expansion load case. Everywhere that's red in my colour scheme is where there's a failure. And for example, around the branch here where 2110 was before, that's also failing in the expansion case. And as you can clearly see, there's almost no flexibility around here. If this T is modelled as rigid, which it currently is, then we have just no flexibility around that area at all. And a few other places as well, there's some failures, and this is the expansion case, and we just simply don't have enough flexibility, but we haven't accounted for the inherent flexibility in these branch connections, because again, the laterals, there's high D over T ratios, just areas where the design code B313 is falling down. It's not, excuse me, it's outside of the range where B313 is or acknowledges that it's inaccurate. So obtaining more applicable data is really something you would look at if you had a situation such as this. And that's what FEA Tools does. It provides that more applicable data very, very easily. Now, for those of you that are following along, if we run this through the FEA translator, it's going to take around 15 minutes to run. There are 11 intersections which need to be analysed, so it's only around just over 1 minute per intersection. But let's set the FEA translation going, and then we'll look at the model in more detail. So I'm going to go to FEA Tools, and the CAESAR II FEA translator is the top button, and it's really, really easy to use. Click that button to activate the module, and here we have 4 tabs. And the first tab is the only one we're concerned with. The other 3 tabs are all output related, so we're not going to bother looking at those until we have some output. They're just going to be empty. So it's very, very easy to use. You need to choose your input file and your output file, and that's pretty much it. You can choose either to convert a CAESAR II neutral file or an actual CAESAR II.c2 or _a file, and you can choose to output the same, either a neutral file or a .c2 file. Other than that, all you need to do is use the browse button. So I'm going to browse for, and if you are following along with the training, you of course need to do the same and locate the file which you downloaded, the FEA Tools customer example. Open the file, and the output CAESAR II file will be stored in the same folder as the original file, and by default it has a -FEA appended at the end of the file name. So I'm going to convert and output to CAESAR II files. And the translation option I'm going to use as FEA, finite element analysis. You also have the option to use 0702 data, which is the correlation equations generated from the finite element analysis and also all the test data during the 0702 project, using the correlation equations, which is much, much quicker. But the FEA, of course, is a full FEA analysis of every single intersection, so it's the most accurate one. It just takes a little longer. And that's really all you need to do. There are some intersection options here. You can choose for the T's, you can choose whether it's a light, medium or a heavy T, depending on the wall thickness. I think during the 0702 project there was deemed to be certain differences between T wall thicknesses from different manufacturers, for example. And these have been classed as light, medium or heavy, so the average T thickness is adjusted slightly, either thinner or thicker for light, medium or heavy. Then all I need to do, and I'm just going to do one thing before I hit the convert button, and if you're following along with me you don't particularly need to do this, but I'm going to deny the FEA library access. And let me explain what that is. Every time you run a model, what the translator will do, it will search through your CAESAR II file and locate any intersections that you specified as a T in your CAESAR II model by ticking the SIFs and Ts tick box. And it will take that, and then using the geometry from CAESAR II, FEA Tools will construct a finite element model of that particular intersection and then run the analysis on that. And every time you run a model, if you have already run that T geometry, say, I don't know, a 12 by 10 inch reducing T, if you run that once, that gets stored into your FEA library. So the next time you run a 12 by 10 inch T, FEA Tools does not need to construct the FEA model and run the FEA analysis on that, let's say, 12 by 10 inch reducing T. Instead, it can go and look up in the library the results from last time. So the first analysis will take longer time. For example, here this one is going to take around 15 minutes. But the second analysis and any subsequent ones of either the same model or any model which has the same T geometries in will take a lot less time. It will just go and simply look up, and it's almost instantaneous when it looks up in the library. Clearly, I've already run this model beforehand when I was preparing for this, so I'm going to actually deny the FEA library access, so I get the same, it takes the same amount of time and I get the same kind of output as everybody else that's following on with me. And then I'm just going to hit convert, and the FEA run will begin. Now that, as I say, that's going to take around 15 minutes or so. So while that's happening, let's take a look closer at the system. The main problem is that lateral around 180 and the branched around 2110. They were the ones which failed in the sustained load case. And on the expansion case, the main large header, there's a number of laterals, and each one of these is currently rigid, so there's no flexibility. And this is why we have all these failures, as I explained when we were searching through the model. Now, we can get a good estimate of these flexibility factors for a T without performing the full FEA run, using the correlation equations from 0702, and FEA Tools provides a module for this. FEA Tools, here it is, the New Branch Connection SIFs and Ks module, or PRGIK. And here we can see the SIFs and Ks from 0702 compared to B313. So let me focus on, I haven't got the file open, so here we go. I'm just trying to open this PDF. Here we go. Page 8. So this area here, this is our node 2110, where we have the failure, and because there's just no flexibility around here, it's very, very tight area. So let's go to PRGIK, put the geometry of this intersection into the SIFs and Ks calculator and see what we get out. Now this is a 812.8 OD and a 4mm wall thickness, and the OD is a straight T, so the branch is the same as well, 812.8 and 4. And then simply compute the I's and K's can see, it just takes a second or so. And we can compare with 0702, B31.3, 2010 version, the ASME nuclear codes, DNVRP, WACE, EPRI, WIDERA, WRC 497, and also PRG stiffnesses as well. But let's just focus on comparing here the flexibilities, K factors, between 0702 and B31.3. As you can see, B31.3, there's no data in there because B31.3 says these flexibilities are just 1. But, well, that's not really the case, as you can see from the 0702 data. Here, for example, for an unreinforced fabricated T, this is this row here, these flexibilities are significant. In fact, the outplane branch flexibility is 134. The run pipe flexibility is also significant. We have over 10 and 36 for in-plane and torsional. And the run pipe is where the overstress was. So what does this mean? Well, like I said earlier, a T with a flexibility factor of K will give you equivalent flexibility as a length of pipe K times the OD. Now our OD of the pipe is 812 millimeters, and our flexibility factor in the in-plane on the run pipe here is 10. So 10 times 800 is around 8 meters of additional pipe that we can take credit for. With an area so tight as around here, if we could take credit for adding 8 extra meters of pipe, 8 extra meters worth of flexibility, then that will certainly be significant. FEA Tools is going to calculate that flexibility and insert them into the CAESAR II model, and that's what it's doing right now. So while that's going on, I think that's the end of this current section. So I'll be passing over to questions again. Are there any questions so far, Janine or Guido, at the end of this section?
No, I don't have any questions here.
Okay.
So Chris, I think it's a good idea when we make a short break. Is it okay?
Yeah, that's okay for me.
Okay, we start the session, or not start, we make a break till 12 o'clock, okay?
Okay, 5 minutes, yeah.
In 5 minutes.
Fine, yep, that's okay for me.
Okay.
Okay, so so let's break, and I will see you, come back in 5 minutes. I'm just going to mute myself for a few minutes then, and I need to go to the bathroom, so.
Okay.
Okay.
Fine.
All right. Thanks. I'll speak to you in 5 minutes. Of course, if there are any questions that coming, then please, you can still submit any questions and we can sort those out.
Okay, fine.